Okay, let's go to the last part of this lecture, which is about optimization of functions of two variables. So remember what we want to do typically is in finance we might want to choose a weight in a portfolio, in an investment portfolio, say to minimize variance, weights of multiple stocks or more than two. The two we looked at essentially was a one variable problem, but if you have more than two stocks, it turns into a multiple variable problem. If you look at microeconomics, you might want to look at a problem that the firm faces that has multiple products and therefore has to choose multiple production levels so as to maximize its profits, etc., etc., etc. So what we would like to do is we want to be able to maximize functions that are functions of more than one variable, multivariable functions. And the idea is pretty much the same essentially as what we had in spirit, at least as what we had for one variable. So we're again going to look at stationary points because these stationary points are the candidates for extrema, so for maxima and for minima. And in order to look for stationary points, we now do not just have one derivative, but we have all the different partial derivatives to look at, and they all should be equal to zero for a stationary point. So basically that's what this theorem says from which is outlined in chapter 13. It says, now if we have an interior maximum or minimum, and this function f is a differentiable, nice smooth function, then this interior stationary point must be this interior extremum must be a stationary point. So it means that all its partial derivatives, in this case when it is just two variables, the partial derivative with respect to x and also the partial derivative with respect to y at this point, at this maximum or minimum x0 and y0, they both have to vanish at the same time. So these two conditions are called the first order conditions. So you will often see that term first order conditions in economics and finance texts. Basically just means look at all the first order derivatives. They all have to be zero for an interior extreme point, minimum or a maximum. Now, of course, this goes one way. So if we have an extreme point, then it must satisfy, if it's interior, must satisfy these first order conditions, but not the other way around, because we might have stationary points, a point should satisfy all the first order conditions, but which are not extreme. And also, at the real maximum or minimum of a function can actually, again, like before, be located on the boundary of the domain rather than interior. So that's another point to be careful about. So just to give an easy example, so supposing we have this function f of x and y, which is just minus x squared minus y squared. Now can we find, and well, this might be, the domain for this function might be the entire plane of real numbers x and y, right? So it's called plane of x and y's. But can we find a stationary point of this function? Well, what is a stationary point? It's a point at which both partial derivatives vanish. So what's the first partial derivative? Df dx, let's just take the partial derivative with respect to x. Well, for the first term, this gives us minus 2x. For the second term, it does not depend on x, so we treat y squared here as a constant if you're looking at the x derivative, so that vanishes. So we just get minus 2x as a derivative, and setting that to 0 gives us minus 2x equals 0. That's the first order condition. And similarly, the second first order condition says, well, the dy should be 0 as well. So this part is going to vanish if I take the y derivative. But again, this gives me the minus 2y, so minus 2y equals 0. And now I'm asking, can I find an x and a y together which solve both these equations at the same time? And you can easily see, well, there's just one combination of x and y that solves both these equations, both these first order conditions, because that means x must be 0 and y must be 0 at the same time. So there's just one stationary point here, point x comma y equals 0 comma 0. That should of course not be a surprise, because if we look at this function, it is actually a fairly easy function in the sense that we can immediately see, well, this x squared, for whatever x is, it's going to be, it's a square, so it's going to be positive or 0, and similarly y squared is positive or 0. So if we have minus x squared minus y squared, this is always going to be a negative number, except of course when x and y are both 0 at the same time. And you see this also in the plot of this function. It's basically this inverted parabola, but now in a two-dimensional parabola, if you wish, which just has this one particular maximum, namely when x and y are both 0, then this function is 0, and for all other x and y, this function actually is going to be negative. So indeed, the first order conditions here indeed identify the unique maximum of this function, x comma y equals 0 and comma 0. So in general, you might be worried also about second order conditions. You might have to look at those. So we saw in one dimension, well, if we want to have an interior, at least local maximum or local minimum, we could at least say something about what's the second derivative of this function. What does that look like in this the neighborhood of this local stationary point? For more dimensions, this is more complicated because there's multiple second derivatives, right? We have to take two derivatives in the x direction, or two derivatives in the y direction, or even mix those up, one in the x and one of the y directions. And you can have multiple possibilities here, and this one is an easy one. Here we really have a maximum point. It's the example we just had. But this one is a lot more complicated, because if you look at 0, 0, which lies approximately here, this is what's called a saddle point. So in one direction, and actually in the y direction, you see it's locally maximum, but in the other direction, the x direction, is locally minimal. And you can see this looks indeed a little bit like a saddle, so this name saddle point is perhaps not surprising, but this is neither a maximum nor a minimum. So you have more options basically to choose from if you look at second derivatives. We won't go into the precise second order conditions that we need in more dimensions, but just be aware that it's a bit more complicated than in one dimension. So, but forgetting about that, so if we are told that there is actually an interior minimum or an interior maximum, then we can actually work with that, because if we know there is an interior minimum, for instance, then we know this minimum must be characterized by both first order conditions being equal to 0, essentially. So let's look at an example where that is actually the case. So here we again go back to this minimum variance portfolio problem, but now instead of having two stocks, we have three stocks. We have a stock A, we have a stock B, and a stock C. And we are asked to invest our investment portfolio in a combination of these three stocks. And we therefore have to determine what weight of our investment amount are we going to put on stock A, what's the weight that we'll put on stock B, WB, and what's the weight that we'll put on stock C. Well, that will then be the remainder, given that we have to invest actually the total 100% or 1 unit of investment money that we have available. So WA and WB are to be determined, and then the WC, the weight that we'll put on stock C, will be the remainder, which will be 1 minus those two weights, WA minus WB. So how do we want to invest those stocks? Well, the question here is, can we find those weights that are going to minimize the variance? The variance again here is similar to what we had with two stocks. So here we just add up the weight squared times the variance squared of each individual stock. So what is the variance when we choose weights WA and WB, and therefore by definition essentially the weight of stock C will be the remainder, 1 minus WA minus WB. The total variance of that portfolio will then be the weight squared of the money that we put in A, so some number between 0 and 1, squared times sigma A squared, the variance of stock A, plus the weight that we put on stock B squared times the variance sigma B squared of stock B, plus the weight that we put on stock C squared, which is using this equality here, just 1 minus WA minus WB, brackets squared, times the variance sigma squared for stock C. So we're going to assume, of course, all those stocks have positive variance. And we're also assuming in this expression that these stocks are not at all correlated. So all correlations are 0 between those stocks. Now we are going to assume that there's going to be an interior minimum. So an interior minimum, again, means, well, in this case, our weights will be numbers between 0 and 1 for each of these stocks. And we're going to assume there is some, for each of these stocks, a weight that's strictly between the 0 and 1, so it's interior to this interval. That's going to solve for the minimum variance portfolio. So if there's an interior minimum, if we are told that, and we know, well, so that interior minimum, these weights there should satisfy those first order conditions. So if we want to find it, well, what remains to be done is find the stationary point. Find the stationary point, or in other words, determine the first order conditions both for the parameter, the variable WA and the variable WB, because searching, optimizing by choosing WA and WB. Remember the sigma A squared, sigma B squared, sigma C squared. They're just givens, right? They're parameters in this equation. The real variables that we are sort of minimizing over are the WA, the WB, and then WC, which is actually given in terms of WA and WB. So we have to find first order conditions for these variables, WA and WB. So they are the things that, in the previous slide we called X and Y. Yeah, they're called WA and WB. So these will be two first order conditions. The partial derivative with respect to WA should be 0. The partial derivative with respect to WB should be 0. Those are two conditions on WA and WB. So we have two equations here with those two unknowns, WA and WB, and we should be able to solve those two equations in terms of two unknowns. We already did that in the first lecture, essentially. So that's what we will do, and we'll do that on paper. So let me go to the paper. So let me write again the problem. So the function that we want to minimize here is this variance. The function of two variables, WA and WB, and it looks like this. It's a quadratic function, actually, WA squared times sigma A squared plus WB squared times sigma B squared plus WC squared, which was nothing else than W1 minus the weights A minus weight on B squared times the variance of the third stock C. So this we want to minimize. We know, or assuming there's an interior minimum, so we want to figure out the stationary point. So what does the stationary point do or mean? Basically, it's the point at which both partial derivatives are going to be 0. So this is the first one. And if we carry that out, so let's have a look. This is a function of WA and of WB. Those are the two variables. Remember again, these other bits, the sigmas, are all parameters of this function. So it's just constant, essentially. It could be anything, but the positive sigma A squared is, of course, a positive number, but we don't really care what number exactly. So we have to actually take the derivative of the variance with respect to WA. Well, the partial derivative of this first term is going to be 2 times WA, because we have a square, WA squared, so 2 times WA times this constant, right? So times sigma A squared. So what about the second term here? Do we see any WH in the second term? No, we do not. So from the point of view of a partial derivative with respect to WA, this is just constant, so it doesn't contribute. 0. The third term, though, does have a WA in it, so we do have to take the derivative with respect to WA of this third term. So it is 1 minus WA minus WB squared. So in essentially we again have to use the chain rule here. So the interior bit is this function 1 minus WA minus WB. So the contribution of the interior derivative will just be the minus, because of minus WA. And the exterior function is squaring this thing. So right, taking the derivative, we then gives us this bit. So this is the derivative, and it should be the partial derivative with respect to WA, and it should be 0. That's the first order condition. Now, that's not the only one. We also have to satisfy at the same time the second first order condition. So the first order condition with respect to WB, almost the same, of course. So the first term here does not depend on WB, it's just a constant. If we take the partial derivative with respect to WB, it vanishes. Second one does depend on WB, so simply gives us this bit. And the third one, again, using the chain rule, this is minus in front of the WB, so we get a minus from the derivative of the interior function, and then we have to multiply by the derivative of the exterior function, which again is actually the same form as we had before. And it has to be equal to 0 for a stationary point. So this basically are the two first order conditions. 1, 2, two first order conditions. They are conditions, there are two equations in terms of two unknowns, because what are the unknowns? They are WA and WB. And the other stuff here, so particularly sigma A squared, sigma C squared, sigma B squared, they are all just constants, parameters. So the question is, can we solve those two equations at the same time to find, well, what WA and what WB are going to satisfy those two equations at the same time? Two equations in two unknowns. Can we do that? Well, of course we can do that. That's what we learned earlier on already. So we can do this, for instance, by elimination, if you remember, or by substitution. By elimination here, in my view, is the easiest way to go. So let me rewrite those two equations again, just to bring out the structure more clearly by getting rid of those brackets. So the two equations, first equation is 2WA sigma A squared minus, now I'm getting rid of those brackets, minus 2 sigma C squared plus 2, I think minus 2 times minus WA gives me plus 2A sigma C squared plus likewise 2 WB sigma C squared equals 0. That's the first equation, and similarly the second equation gives us something which looks almost the same. So plus 2 WA sigma C squared plus 2 WB sigma C squared equals 0. Now I want to figure out what WA and WB are, so let me take together actually the terms that have these WA multiplying them and the terms having WB multiplying them, and let me divide everything actually by 2. Just to get rid of it, because you can see there's 2 in each of these terms, so dividing the whole equation by 2 should still, that's of course makes things simpler. So which terms have WA? Well, the first term and the third term here. I'm dividing by 2. So I get WA times sigma A squared plus WA times sigma C squared. Those are all the WA terms. Then what are my WB terms? So again, I have divided by 2, so I'm losing the 2 here. So it just gives me plus WB times sigma C squared. And finally, I have with a sigma C squared on the other side equals sigma C squared. Second equation, similarly, let me first gather together all the WA terms. Well, there's only one, this one, dividing by 2, so WA times sigma C squared plus, now what are my WB terms? I have WB times sigma B squared in the first term, and I have a WB times sigma C squared from the last term. And again, I'm taking this sigma C squared and dividing by 2. Remember, I take this minus sigma C squared to the right hand side, so it pops up on this side. So now I want to eliminate either WA or WB, so ultimately I want to do both because I want to solve for both. But I'm going to eliminate for you. I'm going to eliminate this WB term. So how do I do the elimination again? So I want to make sure that by multiplying by some appropriate factor, the multiplication constant in front of the WB in those two equations are going to be the same, because then I can conveniently get rid of that term. So how do I make those two factors? So here the multiplication factor is sigma C squared. Here the factor that's multiplying WB is this sigma B squared plus sigma C squared. So how do I make those two the same? Well, I'm going to multiply this first equation by sigma B squared plus sigma C squared. And I'm going to multiply this second equation by sigma C squared. So let's do that. So what do I get? Equivalency again. Multiplying the first equation by sigma B squared plus sigma C squared. So to multiply each term here by that amount. So for the first term, I'm multiplying that by sigma B squared plus sigma C squared. The second term I'm multiplying by that amount. Sigma C squared is what I already had, and I'm multiplying by this sigma B squared plus sigma C squared. And that equals, I also have to multiply the other side by the same amount. So I'm just multiplying every term in this equation by the same expression, which needs to be positive with a non-zero at least, but it is non-zero because those parameters are non-zero. That's what we assumed. So this is the first equation after multiplying everything out by this first factor. The second equation I'm going to multiply by WC squared. So what do we get? WA times W sigma C squared times sigma C squared. So sigma C to the power 4 plus WB times this factor sigma C squared times sigma B squared is sigma C squared times sigma C squared. So that's sigma C to the power 4. So now we have what we want, because these two WB was one of those two variables that we want to solve. They now appear with in exactly the same form, so with exactly the same prefactor, which is precisely what we wanted to obtain. So now we can eliminate. So elimination basically now means just subtracting those two equations. So what do we get? Well, the WA terms give me, just work out those two brackets here. So the first part is going to be sigma A squared, sigma B squared. Let's take the first term here times the first term there. Then we have sigma A squared times sigma C squared. I have the second term here times the first term there. That's sigma b squared, sigma c squared. And I have sigma c squared times sigma c squared, which is sigma c to the power 4. Then I'm going to subtract the second equation, which also gives me a WA times sigma c to the power 4. So those are cancelling. So that's all that remains in terms of WA is when I do the first term here minus the first term here is this combination. Second terms are exactly the same. So if I subtract them, I just get 0. And then for the third, that's precisely what was the goal of this whole exercise, of course. For the terms on the right hand side, I have sigma b squared, sigma c squared, plus sigma c squared, which is sigma c to the power 4, minus sigma c to the power 4, so that's vanishing as well. So this is it, essentially. So now we are in business because we have now an equation from which WB is eliminated. It only has WA times some expression in terms of the parameters is some other expression in terms of the parameters. So can we solve this? Yeah, obviously we can. Just by dividing this by this expression, which is actually again non-zero. So where is it? The right hand side, sigma b squared, sigma c squared divided by sigma a squared, sigma b squared plus sigma a squared, sigma c squared plus sigma b squared, sigma c squared. This is the answer for WA. We also have to solve for WB, which you could do by plugging in WA in this formula. That gives a lot of work, but you can also notice you could do exactly the same elimination procedure on WB, and actually computations look precisely similar, and actually these formulas are sort of remarkably symmetric, so you can already sort of guess what the answer of that should be. So you see here we have sigma b squared times sigma c squared in the expression for WA. Well, likewise, the expression for WB, we will have sigma a squared times sigma c squared in the numerator, and all these different cross products in the denominator. But I encourage you to verify this by just doing the elimination of WA yourself, just to practice how this works. So these two equations, they define WA and WB in terms of the parameters, and if you take a look at this, you will see that indeed these are numbers in between 0 and 1, as they should be. So these two variable values solve both first order conditions. That's what we wanted. So we wanted a WA and a WB, a pair, WA, WB, which solves both first order conditions at the same time. That's what we've been doing here. So this is combination of WA and WB is going to be a stationary point of this variance function because it solves the two first order conditions. We are given that there is an interior minimum, so this is the only stationary point actually that we found, so this must be that interior minimum. There is actually a briefer way to do this. So this is basically this is the general solution, and we are fine. So this is the end of this exercise, if you wish. But we can now see, now that we see the solution, we might have even been able to find this a bit quicker. Let me first note that we can actually write these equations. I agree they look a little bit complicated in terms of all these various parameters, these sigmas. We can actually write them a bit more nicely by noting that WA times sigma A squared, so I'm multiplying both sides here by sigma A squared. Let me just do that. To multiply the numerator by sigma A squared. Now you see the squares of all three sigmas, so the variance of A times the variance of B times the variance of C. Here I had this sigma B squared. This denominator. And now you see that if I do the actual, if I divide both the numerator and the denominator by this combination, sigma A squared, sigma B squared, sigma C squared, of course the numerator becomes 1 if I divide by the same number. If I divide each of the terms here by that same combination, well, for the first, well, if I divide sigma A squared, sigma B squared by this combination of these three, you see these sigma A and sigma B squared are going to drop out, so what I'm left with is 1 over sigma C squared. For the second one, likewise, it will be this, and the third one, it will be this. This looks a bit easier on the eyes. It's a nicer expression, but moreover, the same expression that I get if I compute WB times sigma B squared. And actually it will also be the same as WC times sigma C squared. So we see that these three expressions in the optimum actually have exactly the same form, namely this particular form. And that suggests sort of the easier route. So let me take the easier route by looking once more at the first order conditions here. So of course we solve this in terms of WA and WB, and so actually plugged in already that we know that WC is the remainder, so 1 minus WA minus WB, which is actually what you see here, right? So this is 1 minus WA minus WB. So in other words, what this is WC times sigma C squared. So this first order condition actually was the first order conditions. Could have been rewritten here immediately, like the first one. If I divide by 2, it says WA times sigma A squared, this thing should be the same, bring this term to the right hand side, as WC, which is 1 minus WA minus WB times sigma C squared. And from the second equation, we see that this actually is also the same as WB times sigma B squared. So indeed, these three expressions are, we can already see, should be the same from the original first order conditions. Well, the same is not completely solving it, so we still need to find out, well, if they are the same, how big are they, because that's not that's what we need to know as well if we want to solve this immediately. But if I just call this, give this number a name, so on the side I give this just some number k, it will be some positive number k. What I know as well is that WA plus WB plus WC, the sum of the three weights needs to be 1, right? I'm investing everything in my all my money in these three stocks. So from this I learn that this constant which I'm after, this value that I'm after, is just k over sigma A squared plus, which WA is k over sigma A squared plus k over sigma B squared. WB is k divided by sigma B squared, and WC likewise is k divided by sigma C squared, or in other words, if I take the k out of the brackets, it reduces to this. So now I can of course solve what k is, so this should be equal to 1. So k equals 1 divided by 1 over sigma A squared plus 1 over sigma B squared plus 1 over sigma C squared. So this indeed is, this k is exactly this, WA times sigma A squared. So this is an alternate route for this particularly symmetric problem to have found the same solution. But let me emphasize, this is just to satisfy our curiosity. The general solution, how we get there, is basically what I've outlined here. Okay, so let me get back to the slides then. So we wanted to find again the minimum of these of this variance by working with WA and WB. So I had to again take the first order conditions. So partial derivatives need to be set to 0, and both these equations need to hold at the same time. So here is this whole manipulation that I did on paper, and it's easier to follow on paper than on the slide, I can imagine. So we found these solutions, and that I just also presented on paper, and I noted that indeed this has a sort of slightly more elegant form in the sense of W for each of these A, B, and C times the sigma, or for each of these A's, B's, and C squared are actually the same number, namely that expression that we see down there. And this fast solution that I just showed you, that's on this slide. So that's essentially the end of this lecture. So there's still some solutions to exercises that I mentioned in some of the previous videos that you can first do, of course, and then check on these slides whether you agree with those solutions. So see you next time.